Take it away.
Okay, so thanks for the introduction. So I'm Masato Asahara. So I'm very happy to talk about our latest novel technology, which automates predictive modeling on Apache Spark. So first, let me share the agenda of my talk. So this talk actually does not focus on the very big data, so terabyte or big petabyte data scale model running, but it focuses on the massive number of predictive modeling processes. So actually, so let's say data scientists, okay, first produces one simple logistic regression model to predict the channel of the service. Then so the accuracy is okay, but not so good, but data scientist has to improve the accuracy. So he will try to change some parameters to improve the accuracy. Then so he will produce another logistic regression model. Then so the accuracy is getting better. And then so the data scientist has to try another predictive model type. For example, decision tree. Then, so with different hyperparameters of them and different data preprocessing strategy or something. Then, so after that, so a data scientist has to produce a bunch of number of predictive models, for example, hundreds or thousand scale. Then, so it will take much time to achieve a high accurate predictive model and the prediction results. So then, that is Cumbersomeness I'm just talking. So our technology named NHC Automatic Predictive Modeling releases us from the pain. So it fully automates that predictive modeling processes, and it automatically explores the massive number of predictive modeling processes, and it produces a high accurate predictive model automatically at high speed. To achieve the high execution performance, we have to address these three technical or design challenges. So I'll share the detail of and how to address them in this talk. And in addition, I'll share one Spark technical tip which enables us to run the Spark application stably. And finally, I'll share the experimental results which demonstrate the efficiency of our technology. Okay, so let's get started. So first I'll share the background of our technology. So here, as you know, artificial intelligence or AI has completely graduated research and toy stage and gets into practical use. So emotions of AI, especially predictive analysis, are leveraging many fields of enterprise application like listed in these use cases. However, behind the development, so predictive modeling requires much effort for the data scientists because the predictive model design is still black art. So data scientists had to produce a high accurate predictive model, data scientists had to do these three processes actually. So first process is algorithm selection. So data scientists had to determine the predictive modeling algorithm because so now a deep learning model has a great attention to its high accuracy performance, but many business use cases require the reason why the predictive model predicts that value. Then so if we use a deep learning model, then so this is a kind of a black model of prediction. Then so we don't understand the reason of the prediction results. Then so many business use cases requires to balance the accuracy and transparency of predictive model. Then, so this is one of big headache of data scientists. The second point is hyperparameter tuning. So data scientists have to tune the parameters to extract the possibility or potential of modeling algorithm or machine learning algorithm. And the third point is feature selection. So data scientists usually choose features, good features, which are highly correlated to a predictive target to produce a high accurate predictive model. Then, so these three processes require very high skilled data scientists like PhD class. So even if we luckily have or employ such a very good genius guys, it still takes a long time to achieve or arrive a high accurate predictive model. So then we develop NEC automatic predictive modeling technology, which fully automates these three processes. And so then it can produce a high accurate predictive model automatically. So here, so the technology explores a massive number of modeling possibilities to produce a high accurate predictive model. So from these three aspects, so the first aspect is data preprocessing strategy, including so standardization or normalization of data, missing value imputation policies, random sampling policies, and so on. The second point is algorithm selection. So this technology automatically explores the linear predictive models, decision tree models, our unique predictive model named heterogeneous mixture learning, and ensemble model of them. Especially, so this technology uses a very novel machine learning algorithm to perform the feature selection automatically. And the third point is hyperparameter tuning. So the technology should explore the much combination of the parameter settings, including regularization parameters for feature selection, initial depth of tree models, maximum number of relative features to be used predictive model, and so on. Then, okay, so now we should easily imagine that so the combination of these aspects easily grows an explosive scale, like hundreds or thousands. So if we perform this process on only one single server, then so it will take very long time to complete this process, like days or weeks. So to accelerate the voyage, we leverage Apache Spec. So we implement this technology as a Spec application by leveraging a map-reduced computation model of Spec. Then, so the system can complete the Explorer in less than hours. Now, so this diagram illustrates the modeling and prediction flow of the system. So a user first inputs the training data for model training, validate data, and validation score for model selection. And then, so the system automatically produces a bunch of predictive model candidates, and it calculates the validation score by using the validated data, and it automatically chooses the best model based on the validation criteria. After that, so once the system produces the best predictive model, then a user can produce a prediction results by inputting the test data and the chosen best model. Okay, so now from here, let's dive into the design challenges and solutions of our technology. So here, so to achieve the high performance of the technology, so we have to address these three design challenges. First one is mini-gap integration. The second one is parameter-aware scheduling. And the third one is high scalability. So from here, let's have a look at them one by one. So first, let's dive into the first one. So to achieve the high execution performance, okay, so integration of high-speed distributed computing architecture of Spark and high-speed native implemented machine learning engines is a good idea. But okay, so just saying integration or combination of them is very easy, but however, there is a very big implementation gap between the Spark and typical machine learning engines. Okay, so as you know, Apache Spark is a distributed memory architecture. It's map-reduced computation models, and it's implemented as a Scala program which runs on Java virtual machine. On the other hand, so a typical machine learning engine is designed as a single or shared memory architecture. It uses a standard computing framework, and it's a high-speed native binary code. So to implement the system on Spark, so we have to decide the design, implementation design, which fills this big gap. To address this issue, we choose mini-gap integration design, which smoothly bridges the distributed preprocessing part and parallel execution of the machine learning engine. So here, this diagram illustrates the training phase of the system. So first, the system reads the training data from HDFS, and it performs the data preprocessing, including standardization or missing value imputation in the map-reduce phase. After that, so it applies the downscaling of the training data by using a random sampling algorithm, so that the training data fits to the one server's memory because we have to improve the parallelization, execution parallelization of machine learning engine is a big important in this case. So then this system converts the random downscaled training data into a matrix-based RAD whose element is a matrix object. After that, so the system runs the machine learning engine in map operation of Spark, and then so the machine learning engine produces a bunch of predictive models candidates into HDFS. This figure illustrates a validation phase. So, okay, similarly, so the system reads validated data from the HDFS, and it performs the data preprocessing done in the training phase. After that, so different to the model training phase, the system divides the validated data into partitions, and it converts matrix-based RDD whose element is correspond to a part of data frame validated data. After that, so the system runs a machine learning engine with one model and produce in the servers, and it produces several paths of prediction results. And then, so the system converts the partitioned matrices objects RDD to a one data frame RDD, and it calculates a validation score. And so the system repeats this prediction by the predictive model and aggregates partitions into one data frame and calculates the validation score in the MapReduce program. And then, so it chooses the best model based on the validation score. This is a prediction phase of the system. So this is very similar to a validate phase, except the model selection phase. So let me skip this, the detail of this phase. Okay, so let's move on to the second challenge, parameter-aware scheduling. So in this system, so if we choose a naive implementation design or scheduling algorithm, then so it requires a multiple data load and convert, and it degrades the execution performance. So let me share the one example with this figure. So if we choose a scheduler which assigns the multiple matrices for model training and one set of hyperparameter values, then so this design requires a server to load multiple matrices from other servers, and it multiple conversion from the data frame object and to the matrix object. Then, so this design induces a waste of memory, load of data from other servers, and multiple data convert to matrix. So then it increases the execution time. So to avoid such a performance degradation, we choose parameter-aware scheduling. So that means, so this scheduling algorithm assigns one or a few matrices to every server. Instead, so it assigns the bunch of hyperparameter sets, theta 1, theta 2, theta 3, theta 4, theta 100 something to every server. Then, so this with this design, so a server can use matrix, reuse a matrix object among the several hyperparameter candidates. Then, so this design achieved efficient memory usage, low load of data from other hosts, and low frequency of data convert to matrix. Okay, so now let's move on to the last one. So high scalability. So in this situation, so the system, okay, so produces hundreds or thousands of models at once. So it's very important to improve the scale out or scalability property of the machine learning engine execution part. Because so the execution time consists mostly of the machine learning execution part. But if we choose a very bad scheduling or naive scheduling algorithm of the machine learning engine, then so it degrades the execution efficiency. So let me share one example with this figure. So in this situation, so the above server is assigned to complicated model training. Then so the server takes 10 minutes to complete the model training of two models. On the other hand, the below server is assigned with a very simple, lightweight model training, for example, decision trees or linear models. Then, so the below one takes only 2 minutes to complete the model training. In this case, so the below server has to wait 8 minutes in the idling state. Then, so this is very inefficient resource usage of the cluster, right? So to improve the efficiency of resource usage and improve the scale out property of the system, we choose predictive scheduling algorithm. So that is which balances complex model running assignments and simple one assignments. So here now, so the scheduling algorithm assigns complicated model training first to the every servers. After that, so the scheduling algorithm assigns the right weight model training to the servers. Then, so the model training task assignment is expectedly balanced among the executor servers. Then, so this is improves the resource usage efficiency as much as possible. All right. So now, let me share one practical Spark technical tip which enables us to run the Spark applications stably on YARN. Yeah, actually, so we are using YARN to run the Spark application to run the multiple these systems with different prediction problems and different data. In this case, so we have encountered very mysterious out-of-memory errors, even if we gave the much enough memory to the Spark executions and Spark executors. So in this case, so finally we found the reason of this failure. So that is, so the default configuration related to the resource assignment of Spark fails the execution because so the Java virtual machine system memory suddenly spikes over the YARN limitation. So this chart illustrates that phenomenon. So at the end of part, so this timing, so the memory usage of Java virtual machine exceeds the YARN limitation. Then, so the YARN notifies, okay, so this JVM process violates the limitation, memory limitation. Then, so it kills the process, and then it fails the Spark execution. This problem is not a special case in our case. So because, this is already reported at last year's Spark Summit. Then, so I believe you may encounter these failures if you are using YARN. So to avoid such an annoying situation, we have to carefully configure the memory overhead property of Spark. Actually, Spark user guide suggests us to configure this property with 6 to 10% memory overhead of memories of executors. But unfortunately, in our case, we have to give the 15% overhead of Spark executor memories. So this is not so small size, right? So actually, we do not say that we are using the memory efficiently. So we are still investigating how to reduce this overhead memory now. All right, now, so evaluation. So our evaluation will demonstrate the efficiency of our technology, and it can complete the process at high speed. So in this evaluation, we compare the top 10% precision of targeting the potential positive sample between our technology and manual predictive modeling using scikit-learn. And so manual predictive modeling basically uses the default parameters of scikit-learn in order to simulate a newbie of data science. And this evaluation uses a real data set used by the real competition of KD Cup 2014, 2015, and EGKI 2015. And so our evaluation was done on our very special, unique, compact cluster machine named Scalable Modular Server, or DX2000. So this machine, this compact 3U machine consists of 34 server modules, which employ 270 high-speed G-only processors, 2 terabyte memory, 34 terabytes SSD, and 10 gigabit Ethernet for internal network. So actually, this machine has the advantage of memory, high-speed memory access. So I believe this is a very good one of hardware for Spark cluster construction. Okay, now, so this is the results of the evaluation. This is the evaluation results. So in this case, NEC automatic predictive modeling produces competitively accurate models automatically. So it produces up to 3% more accurate predictive model compared to the a manual prediction operation. And it completes less than 3 hours, up to 3 hours, the process. So please give attention. So this accuracy was produced in fully automation of the modeling processes. Then, this technology releases technology gives much time to focus on much time for data scientists to focus on the more important tasks. For example, design of the prediction problems or feature engineering or others. Okay, so now let me summarize my talk. So in this talk, I introduced the NEC automatic predictive modeling technology, which fully automates the predictive modeling processes and by leveraging Spark high-speed in-memory computing architecture. And to achieve high execution performance, we have addressed these 3 design challenges. And now, we are working on the 3 typical future work topics. So the first one is to extend to other models to improve the more accuracy, like deep learning models of TensorFlow and others. Second one is as already I told, so to reduce the young memory overhead. And the third one is speed up topics. So we are investigating how to leverage modern processor technologies, including FPGA, GPU, and other vector processors. Okay, so that's all. Thank you.
Thank you, Masato. Do you have any questions? If so, raise your hand, and I'll run around and let you guys get the microphone. Any questions? Because we are almost at time. Okay, I think if you do have any questions, Masato will be just out there at the back, and please give him another round of applause.
Thank you.